would love to just hear like a high level overview on why Monad database is kind of different from other databases, why it's important to not just use a standard like PebbleDB or RocksDB implementation when trying to build a performant EVM. Like, what's the role of the custom state database here?
Yeah, so just to step back for a second, the most expensive parts in the blockchain are your cryptography functions, your elliptical curve cryptography, your hashing functions, your state access, even the most complex business logic in most smart contracts is actually um, pretty pretty cheap compared to execute compared to programs that you might find like on your desktop or on your phone. So there's just not a lot of computation currently in modern blockchain. So parallelizing computation by itself doesn't really gain that much. Some clients already have parallel sender recovery, which is one of the most expensive parts of transaction execution. So there's not much to gain really there either. You can throw multiple cores. It's kind of a trivially parallel problem. So when we started like profiling the code, we started seeing, okay, where is the time actually spent? You will see that the database, like just a single read from an SSD, has latency of maybe like 80 microseconds to 100 microseconds or more, depending on what model you have, obviously, what generation, all that sort of. There's all sorts of parameters there, but it's still like orders of magnitude longer than it takes to execute like a simple smart contract. So you'll have multiple reads. You'll have, you're obviously going to read the sender's account because you need to know their balance. You're going to read the destination account. If there's a proxy account, you got to read that. So you're going to jump a couple accounts. You're going to read slots. If it's ERC20, the data is actually stored in storage slots. Your balance is stored in storage slots. If it's Uniswap, there's other sorts of storage there. So if you just kind of like do all this read sequentially, and it's 80 to 100 microseconds, we're assuming here it's not cached, right? In main memory. So you kind of sum these all up. It's just like a linear chain of summation of long times, and it ends up being a long time to execute just that single transaction. So obviously, you could just throw RAM at it, and you could say, I'm just going to require that everyone has a very large, expensive box that sits in a data center somewhere and will never actually read from disk. So there'll be no latency and everything will just go very fast. That's one option. But I think, you can still achieve good performance if the code is right and you can extract performance out of the SSD. And modern SSDs, a $200 SSD is an amazing thing these days. Like everybody should be super impressed with whoever is designing and building this hardware because it's super good hardware. I'd like to like meet some of these people someday at Samsung or wherever that they're building this stuff. But it's just like super impressive. And then you take like that raw performance and you see what like some of these other databases are doing that people are using for blockchain clients, and the performance is terrible. So like what went wrong from starting with like something that's very high performant and ending up with like this terrible sort of performance. And obviously one of the first issues that the Geth has is like you're embedding one data structure inside of another one that's on disk. So you kind of have this like every request is traversing basically sort of two data structures, and it's just a very expensive operation. There were some other innovations around this. People tried different databases. You have B plus tree databases like LMDB and MDBX, which is LMDB derivative. You have LSM trees like RocksDB, LevelDB, I think was the first one actually. RocksDB was a derivative, and some others like that. They each these are just general. The problem with these is they're general databases. So, they're just meant for somebody to download. You want to like store some data, request, do some searches, this sort of thing. General data structures, just general application code, just is not performant. It's just meant to be performant on average. So if you ever work in like HFT, this is something you'll quickly discover is like, nobody in HFT uses standard libraries, standard C++ libraries, or standard because these are general sort of data structures. If you customize the data structure to the trading model, you can extract way better performance from the hardware. So we're just kind of applying that technique here, where we know exactly how we want to use the data. We know exactly how we want to store the data. So let's just do it the way it should be done. And that's why we started implementing our own database.
Got you. Yeah, it sounds like from your, I've never heard someone describe SSDs in such a attractive way. That makes me now in awe.
Well, I grew up with like spinning disks, so the old hard drives were like in your computer were very slow, and you had to, the technique back then was like you had to read stuff sequentially because the disk is basically spinning, and you want to like grab it and just read like what's on the disk, sequentially, and so maybe it's just because I'm older, but SSDs are pretty amazing.
No, I mean, it sounds like there is just a ton of juice packed into SSDs that if you customize them to be efficient, you can get massive performance gains over just using the standard model, and standard kind of structures that, seem to be kind of, across the industry, the way that people are typically using these SSDs. So
Yeah,
that,
a modern SSD, like the ones we just got for some of our hosts, are like they're 500,000 IO operations per second. So it's pretty amazing, but you got to leverage that. You can't just you can't throw, one thing you study in computer science is like complexity, right? And an algorithm which has better computational complexity, but is actually more poorly implemented, will still perform better. So you can't just let that, you can't just forget about your optimizations and be like, okay, the hardware is going to take care of it. You're just wasting basically the capability that's there. And so some of these databases, the way that some of the blockchain clients are using them is they're just making so many requests just to look up something basic. And if we do a 10th of the requests or a 20th of the requests, that's how much more requests we're going to get out of the hardware. So, I think in some cases, if you look at some numbers, like MongoDB probably makes 1 or 2 requests to look up an account, whereas if you look at something that's not in cache, if you look at some of the data structures, you may end up making 20 requests to the hardware. So it's just that sort of like super optimization to extract every last bit of performance we can get.